Hello, good afternoon to all. So this is Dr. Dilip Kumar Nandi from SKC Autonomous College, Parlakhemdi, Gajapati, Odisha. First, I would like to thank the 15th Faculty Induction Program is organized by Dr. Babasaheb Ambedkar, Marathwada University, Chhatrapati Sambhajinagar. And today, again, I will be thankful to them for giving me this opportunity to present my some of my work in this seminar. So today I will be talking about one of my recent topic that is titled here. This is probing thermalization phenomena in HGP. Later, I'll explain what is the meaning of HGP in details. Okay, so here is my outline. So first, I'll talk about what is something called Anderson localization and what is the meaning of a single particle problem here. And then I'll talk about what is many body localization. That means how this concept coming from single particle to many body case. Now then I'll discuss different type of numerical approach that is used to study this kind of MBL physics. So this is MBL means many body localization physics. And then recently as I've used one kind of different tool. So then that is based on this adiabatic gauge potential. So I'll be talking about this one specifically in more detail. And then what is the numerical technique that I use to calculate different physics. So this is kind of known as exact diagonal technique before I summarize my talk. So basically I'll be talking about one of the important method that is the adiabatic gauge potential and different kind of numerical methods that I've used, specifically the exact diagonal method to study this kind of localization physics. Okay. So let's start with this single particle localization physics. So this is actually the idea given by a pioneer scientist. This is Anderson localization, for which he received the Nobel Prize in 1957, around 1960, because he published this paper in 1957, and then I think 10 years after he got this Nobel Prize for this. And this is a very simple model. If you can see, it's titled like absence of diffusion in certain random lattice. So here is this Hamiltonian, as we have mentioned, this system in generic, but this is actually a single particle problem. And now he has given like, let's say this first term minus t, and this is ci dagger ci, Hermitian conjugate, plus this epsilon y ci dagger ci. So basically this is like, if you have a system in physics, then you have basically, of course, like kinetic energy and potential energy. So first one is the kinetic energy, so that the particle can hop from one side to another side. And this is, as usual, the kinetic energy term if you write down in a second quantized form. And whereas the second term is known as the on-site potential energy. But what is more interesting is like this on-site potential energy, you can see epsilon I, the strength of each and the on-site potential at each site is different. And it actually is different means it's completely random. So that means uncorrelated on-site potential. So what we actually observe in our solid is like, let's say we have a solid which is very this is periodic. So then one can simply apply like Bloch's theorem and other stuff, because your system is periodic, then your function is kind of plane waves. But here this is not a plane wave, because you're distorting in your on-site potential, so you never know how the system will behave. But that means in general your on-site potential is different. So that means your system or your particle can localize or delocalize depending upon the strength of your on-site potential. So what is so interesting about this fact is like, okay, so as he proposed, like this is kind of a different setup which cannot be solved exactly. So that means you do not have any analytical tool to solve this kind of problem, like the case of periodic system in solid state. So for this, he has written here, one is to restore the ingenuity of numerical simulation to settle even the simplest question about it. Okay, so this is clear. I mean, one do not have this kind of a complete idea by using some sort of analytical tool, but rather this can be tackled only through the this numerical approach. So then let's go up to, what do we mean by many body localization? Of course, the last slide concerned about this, single particle localization. So going beyond that, if you have many particles, then this particle can talk to each other. That means they can interact with each other. So that means the effect of interaction should be there inherently. So that means this is called kind of, the system is now a many body system. So now, what is the meaning of many body localization then? So in case of single particle localization, if your random strength is increased from a certain value, from a critical value, then all then particle will be localized. And if it is lower than the certain value or critical value, then all particle will be delocalized. So here in presence of interaction, then again, what will be the scenario? So that scenario will be if exists, then this is known as many body localization. So here is the statement. This is a kind of new testing dynamical phase of matter which doesn't self-thermalize. That means, you know, this will be localized for forever if it does exist. So then what will be the typical characteristic of this page? So one is like, there will be, of course, no transport of particle. That means zero DC conductivity at finite T. And there is no entanglement between different parts of the system. And this is, of course, Anderson localization with interaction. So then what is the importance of this kind of phase if it exists? Of course, there will be a lot of technological application one will find once this phase is well established. So, for example, in quantum information, and in the quantum memory devices, quantum photonics, and quantum computing, and so on. So then what are the key ingredients that will be dealing with this kind of system? So one is disorder, another is many-body system, of course, and then the third is interaction as well. And the last, but this is the most important thing, one should have this. They should have an isolated system. So these are the kind of interesting property for MBL phase if it has exist in future. So now, what are the standard numerical approach people adopt to this to study this kind of physics? So these are the various things. So first one is the various spectral diagnostic. Like that means if you have a Hamiltonian, you need to solve to find out its eigenstates, eigenvalues, and these are called spectral information. From this one can also get the information about this kind of physics. And this is also there are also theory coming from entrometrics, which is completely from the mathematics point of view. So there is also different theory people have already proposed to study the different physical setup from this kind of context. And there is also recently that people have proposed another theory that is called eigenstate thermalization hypothesis. This is also another tool to find out this kind of physics, to probe this kind of physics. So what are the key issues then that is one need to address? So first one is of course the finite size effect, and then that is the drift of critical disorder strength, and this is the limit, and then this is limitation of classical computer. So these are the different issues. So currently, what is the numerical capability or computational capability we have? Depending on that, these things are already there. So you need to kind of compromise between different setups. So you cannot go beyond a certain number of lattice sites. You cannot go beyond a kind of larger system with different type of disorder strength. So we have to compromise between different parameters. So today I will be talking about a different probe or different diagnostic that is based on adiabatic gauge potential. So this is abbreviated as AGP. So mostly I will be talking about different numerical results based on that. So before going to that, let us discuss one more thing that is actually I mentioned in the last slide. What is the method that is generally related to this endometrics theory? So in endometrics theory, people generally do kind of spectral analysis kind of stuff. So here actually if you have a system and then you solve the Hamiltonian and then you find out the eigenvalue, eigenstates. So this is the kind of information one can get from these two only. So let's discuss about just information what you can get from the eigenvalue. So this is called something called level spacing distribution statistics. So if you draw your level spacing distribution with respect to your distribution type, and here of course your data, then if your data follow like this kind of you see the green curve, and this is called Poissonian distribution. And another is like if your level spacing distribution follows this kind of Gaussian type of stuff, this is called in general like Dyson statistics. So then this will be like kind of different scenario. So these two scenario, what are these two? So if this follow this Poissonian distribution, then the system will is a kind of in a localized phase. And then if your level spacing distribution follows this kind of Gaussian distribution, then this will be like thermalized phase. So even from the simple diagnostic of energy eigenvalue, one can get information uh, about the whether this is normalized or localized phase. So yeah, this is kind of a different kind of, depending upon the symmetry of your Hamiltonian, you have different kind of ensemble. So one can have Gaussian orthogonal ensemble, and then unitary ensemble, and then symplectic ensemble. So these are the different functional form of your the distribution function, which will look like the depending upon the symmetry of your Hamiltonian. Okay, so this is how this is related to random matrix theory and your Hamiltonian. Okay. So now the new tool which I have used in my study, this is called adiabatic gauge potential. So this is basically if you have Hamiltonian and that depends on some external parameter lambda, then if you can solve this eigenvalue spectrum, h lambda equal to e lambda, and this is e lambda is eigenvalue and n lambda your eigenstates. So what you define is something called different a new operator. This is called HEP operator, and this is the matrix element defined by this definition. And then this is, you can see in the right hand side, this delta lambda Hn. And this is, of course, here omega, the energy difference between two eigenvalues. Okay, so this is the Frobenius norm. One can define in this way to quantize or to kind of numerically evaluate this kind of thing. So basically, you have a system. You are perturbing your system by whether you are locally or globally, and then accordingly you can define some matrix element. And this matrix element could be a global operator, could be a kind of local operator. So depending upon the numerical value of this thing, one can investigate how sensitive this Frobenius norm is to this kind of external perturbation. So, okay, so here is one, what is an application of this kind of HGP. So let's quantify this kind of diagnostic using these two models. So here I will be basically talking about two different model. One is integrable model, another is chaotic model. So in case of integrable model, you can see this is a XFG Heisenberg-Spinchen model. So here this is XXY interaction and then this is G interaction. And now on top of that, we have a global term which depends upon lambda. So this is basically your gauge transformation direction. So why this is called integral? Because one can exactly, kind of solve analytically using different tools. So that is why it is integrable model. So another is like chaotic model. This is chaotic easing model. So this is also another famous easing model from famous one-dimensional model from the quantum magnetism point of view. So because this is a chaotic, because we have GG interaction and you have magnetic field, external magnetic field in the z direction, x direction, and again we have some global kind of perturbation along x direction. So both of this integrable as well as chaotic model, they are now perturbed globally. So now we will see what is the response of this system with respect to this global perturbation by quantifying this HGP as I defined in the last slide. Okay, so here you can see we have studied like the system size, lattice size up to 16, and you can see for a chaotic model, that means chaotic easing model, the scaling behavior is like exponential. And for integrable model, this is showing kind of polynomial scaling. So here is the exponential as well as here is the maximum, sorry, this polynomial. So one is having, for the integrable model, this is completely a very slow, kind of not that much sensitive, but for chaotic model, this is highly sensitive. In compared to other diagnostic, one cannot find such type of huge difference in sensitivity to this kind of spectral analysis. So this is one of the, again, a good indicator or good quantifier to differentiate between two different model or two different phases. One is localized phase, another is kind of thermalized phase. Okay, this is nicely explained in this paper. You can see, and we have expanded. We have also, kind of studied this model in our setup using other model also. Okay, so here is my conclusion. So as I said, we found the spectral analysis using HGP and find that this HGP is quite sensitive compared to other diagnostic, and we applied to different model. One is integrable model, for which we found there is this HGP scales polynomially with respect to disorder strength, and for the chaotic model we found the HGP scales with exponential scaling behavior and with respect to disorder strength. And finally, we found that for a free non-interacting model, we found this is in the HGP is insensitive to the disorder parameter. So these are the different scenario we found out for our model, and we studied the HGP is quite sensitive in this perspective. So, and here is my collaborator with whom I did my work when I was in South Korea as a postdoc. and we published a couple of papers based on these things. And yeah, here he is my team leader and other my collaborator. And thank you finally for your kind attention, and hopefully we'll see in the next time. Thank you.